Hello, everyone. Welcome back. Today, I will present Lecture 11, Potential Phase Diagrams and the Clausius-Clapeyron equation. When we talked in the last lecture, we'll talk about the Gibbs phase rule. So today, we're going to talk about the phase regions in terms of Gibbs phase rule. The Gibbs phase rule is represented by this equation. Nu is the number of independent potentials when P phases are in equilibrium. C is number of independent variables, independent components. 2 represents 2 potentials, temperature and pressure. That means in a system we have C plus 2 dimension, the C plus 2 potentials. And it forms a C plus 2 dimension space. So for a single phase region, that means P equals 1. Then we get the nu equal to C plus 1. So that means single phase is a C plus 1 dimension feature in this C plus 2 dimension space of potentials. Now, two-phase region, that means the 2 phases are in equilibrium. Now, we have the 2 single-phase regions. They are each C plus 1 dimension. And when these 2 phases meet each other, they are in equilibrium. That means they have the same potential for each potential. So that means we get one constraint, and then the C plus 2 single-phase regions, which are 2 C plus 1 dimension space features, they intersect each other, form a C dimension feature. That means the 2-phase region is a C dimension feature in this C plus 2 dimension space of potentials. Now you have 3-phase regions. That means 3 phases are in equilibrium. Now I have 3 2-phase regions. And then the dimensionality of the 3-phase region reduces by another one. So it becomes C minus 1 dimension feature. That means as 3-phase equilibrium, the 3-phase region, it only have C minus 1 independent potentials. We call C minus 1 a dimension feature. And you have P phases. You have P phase region. That means P phases are in equilibrium with each other. So you get the intersection of P minus 1 phase regions. Okay. So the number of independent potentials in terms of the Gibbs phase rule becomes C plus 2 minus P, then C plus 2 minus P dimension features. Of course, you can continue to move that forward until you get the C plus 2 phase region. Okay, that means the C plus 2 phases are in equilibrium, the intersection of C plus 2, C plus 1 phase regions. Then nu becomes 0. So it's a 0 dimension feature, a point in this C plus 2 dimension space of potentials. We call it invariant phase equilibrium because no potentials can be changed anymore. They have all to be fixed by this C plus 2 phases. So now let's look at the single phase region. Okay. So talk about the C plus 1 dimension features in C plus 2 dimension space of potentials. So we're going to keep 2M equation. So all the potentials, dt, d minus p, and d mu I, they are not independent anymore. The summation of them equal to 0, whereas this compact form is xa is molar quantities, and the ya are potentials. So molar quantities in this equation represent entropy, volume, and moles. Where the potentials y include temperature minus pressure and the chemical potential of each component. So of course, this multi-dimension space is very difficult to visualize it, but if you take any 2 potentials, that means you fix other potentials. Okay, so that means only two potentials left as independent potentials. Then we get this a simplified form of the Gibbs 2M equation. xa dya plus xb dyb equals 0. Now we can remove to rearrange this equation. We'll get a derivative of ya to derivative YB, then we move XB, YB on the other side, we obtain this equation. Is derivative of YA to YB equal to minus XB divided by XA. And this is less than 0 because more the molar quantities themselves are positive, right? Positive entropy, positive volume, positive mass. So that means the derivative between any two potentials would be negative. So that means single phase region in this C plus 2 dimension space of potentials is convex. But please note that we have this minus P, okay? That's just because the minus P is the surrounding gives the pressure to the system, right? Okay, so that's why it's minus P. So everything is convex for each phase. Okay, so this represents the properties we discussed in lecture 6, slide 54. Okay, now we have 82, so go to 54. So that's the properties we discussed previously, right? So these are the potentials. So the derivatives between two potentials give the properties we measure. As we talked about before, for example, thermal diffusion, stress migration, and so forth in lecture 6, we discussed it. So that means all the properties we measure can be calculated from the derivatives. These properties can be calculated by the derivatives between the two potentials. Okay, so that again shows that, of course, many times we derive models for those properties, but if we have the free energy, then we can calculate them from the derivatives of free energy. So that's a very important part we're going to emphasize a lot in this class about applications. All right, so let's move to next slide. So now we have this single phase, two phase, three phase, C plus 2 phase regions. So we'll make them in the diagram, right? In the diagram. So but because they're all potentials, we call them potential phase diagrams. Again, that was really important lessons I learned from Max Hillard. We start with potential phase diagrams because that's where we talk about equilibrium. Okay, so now remember that we have C plus 2 potentials, but one of them is dependent, right? We only have C plus 1 independent potentials. So that means we want to change from the C plus 2 dimension to C plus 1 dimension. Okay. Of course, you know that we know that because one of them is dependent, so we can take any one of them and remove it by projection. Okay, so we projected the phase regions into C plus 1 dimension. Remember that a C plus 1 dimension is single phase, right? Single phase occupies the whole space. But because it's one dependent variable, the projection will not lose any information. Okay, so C plus 1 dimension will still be C plus dimension. Okay, C plus C dimension will be still C dimension. Now, so single phase region is basically C plus 1 dimension space, as we mentioned before. So it fills whole space. So in this C plus 1 dimension space of independent potentials, we get a single phase. Now, when in the two phase region, then C dimension, right? The dimension decreased. So it's like a hyperline in this C plus 1 dimensional space. Then P phase region would be C plus 2 minus P dimension. And then 0 dimension would be C plus 2 phase region. That is 0 dimension in this C plus 1 dimension space. So it's very important to realize that in this C plus 1 dimension space of independent potentials, all the geometric features are phase regions. There's no phase boundaries. Phase boundaries only occur when we have the molar phase diagrams. That will be talked about in the next lecture. Okay, so that's a very important concept. So in the potential phase diagrams, we only have phase regions. Single phase, two phase, until C plus 2 phase regions. Okay, now because the C plus 1 dimension is too high dimension for us to visualize, so we want to reduce the dimensionality so we can see it. We can visualize it. So then we do the sectional potential phase diagram. What it means is that we fix some potentials, right? That basically section this C plus one dimension space. So if you fix the potential, of course, the number of independent potentials will be changed, reduced by the number of potentials fixed. So we can revise the Gibbs phase rule. Is that the nu equal to C plus 2 minus P minus NS. So NS is number of fixed potentials. So we can fix many of them. For visualization purpose, we go down to 2 dimension. That means I have 2 independent potentials, 2 potentials. Okay, so that single phase region would be 2 dimension. That being area in this 2 dimension space. Now 2 phase regions, that means now two area meet together and form a line. So it's a 1 dimension line. So it's a line. Okay, 3 phase region will be 0 dimension, is a point. So I have an area, line, and a point in the 2 dimension phase potential phase diagrams. Okay, so now we can calculate what the NS would be. NS would be C plus 2 minus P minus nu. Okay, so now you can see that in order to get this, in order to reduce the 2 dimension, okay, that we have to calculate. We have to fix C minus 1 potentials, but in the number of in a C plus 2 dimension space or C component system with temperature and pressure. So now you've got one, and then nu becomes 3 minus P. Okay. So if 1 phase is 2 dimension, 2 phases, 1 dimension, 3 phases, 0 dimension. Now, so geometrically same as 1 component system. Okay, because 3 equals to 1 plus 2. Okay, so that means every diagram we've sectioned into a 2-dimensional potential phase diagram, and then it just behaves like a 1 component system. So then we have this 2 phase region, 3 phase region, and so forth, right? So want to be able to calculate this phase boundary directions. Of course, again, for simplification, we want to calculate the only 2 independent potentials, right? You have C plus 2 potentials. You project to C plus 1 dimension space of potentials. Then you do sectioning. Okay, so let's go into about 2. Okay, 2 potentials, any 2 independent potentials: temperature, pressure, temperature chemical potential, and pressure chemical potential, any 2 chemical potentials. And then we obtain the Gibbs equation like this. And remember that we have 2 independent potentials. We must have another one dependent, right? So for material scientists, at least, because we always talk about the per mole of system. So we take 1 dependent potential as chemical potential. Okay, so we have 2 independent one we want to consider, Y and YB, and we take the dependent one as the mu A. So now we normalize it because each phase has different molar quantities. We normalize it. So we divide NA on both sides. We get X mu A alpha, X mu A B. Oh, this is A and B. Okay. Now we put MA here. It means it's normalized per mole of A. Okay. So that means XAMA is equal to XA divided by NA. XMAB equals to XB divided by NA. So it's if you look at Marcellus' book, it's called a Z fraction if it's mole fraction. So it's normalized to 1 element, 1 component. So because both phases are in equilibrium, right? So they have same YA is the same in both phases, YB is the same in both phases. Mu A is of course same also in both phases too. So the change, if they maintain 2 phase equilibrium on that line, the change should be same too. Okay, but their molar quantities are different. So you get the depth of XMAA and depth XMAB. So, for example, the molar volumes are different. The molar entropy is different. The molar composition with the mole fractions are different. So then we have this equation. We because mu a cancel each other for both faces. So we get the delta x a delta x b. Okay, that dy a dy b. Then just rearrange it. You get this ya to yb derivative equal to minus this difference. So this is very different from the one component system, right? In the one component system, there is no data here. In one phase, so it's one phase region. Okay, potential derivative is also this formula, but there's no data. But now because it's for two phase equilibrium, okay, so we have the data, the difference between the two phases for this molar quantity XA and the molar quantity XB. Okay, now we are very familiar with the Clausius-Clapeyron equation applied to temperature and pressure. Okay, so what does that mean? That means now let's consider a two-dimensional phase diagram, that's a potential phase diagram, dt and d minus p. So I have t and minus p. Okay, so we put the same equation as we before. Now we replace the ya and the yb, and this would be the xa and xb. So this would be molar entropy, okay, molar volume. No, I should have ma here too, right? Because for one component. Now for the component A. Then we get this relation. So now dp over dt. Now because you have minus sign here, so we don't have minus sign here. Okay. So it's delta S and divided by delta V. And now we know that in the stability and the T and S, we talked about it before, for a phase, T and S must change the same direction if the thing is stable. And the minus P and V change the same direction because they're conjugated variables in equilibrium. That means when dt is positive, delta S is positive, right? When dp is positive and delta V must be negative. Remember, I have negative here. Okay, it's conjugated variables. So that means when dp over delta t is larger than 0, then the t and v also change the same direction, right? Because this is positive, and this must be positive. So we get a positive with some expansion. Okay. However, we know that the phase boundaries where this dp over dt of not phase boundaries, sorry, phase regions, two phase equilibrium regions, when dp over dt is negative, then the t and the v will change in opposite directions. Just by this Clausius-Clapeyron equation. Then we say that in the system, the volume, the high temperature phase must have smaller volume. Okay, that means there's a possibility in the system to be negative some expansion. Okay, either for single phase. Okay, the high temperature phase will probably have a smaller volume, right? So that means that in that temperature, somewhere in the TP phase diagram regions, and some expansion could be negative. Okay, so we discussed this one in one of our paper in 2011, and we have predicted from the quantum mechanics, as we will discuss later, in terms of entropy. Now let's give you an example. This again is from the Master's book, his textbook, the beautiful textbook. Now we have three potentials: T, minus P, and mu A. Okay. Now you see that, remember that any two potential derivative gives negative curvature, negative slope. That means the single phase region in this three potential space is convex, right? Because all the directional derivatives are negative. Okay. So this is very nice demonstration of the fundamentals. Now, we want to make a phase diagram, right? Phase equilibrium. So phase equilibrium is that you have one single phase surface in this three potential space. So you have three of them. So two of them you can intersect each other. For example, this would be, you see, this is the beta, right? Beta, okay. You have beta here. You have alpha here. This is the surface, right? And you have gamma here. Okay. Now you see when the beta and alpha area, the two areas, they meet each other, get a single phase, the two phase region here, right? So you have one two phase between alpha and beta. You have between beta and gamma. You have between alpha and gamma. So I have three lines now. And the slope of the lines can be calculated by the Clausius-Clapeyron equation. Now, because this is one of the potential mu A here, for example, is dependent. So it doesn't provide any new information. So we can project this this three-dimensional diagram space into two-dimensional space. Okay, that's what happens here. You project down, you get a alpha and a beta. Okay, you get a beta gamma, you get alpha gamma. Okay, all the geometric features in this diagram are phase regions. There are no phase boundaries. Phase boundary, again, as I mentioned, will come up later. It will show up later when we talk about the model phase diagrams. Now you see, you have three-phase equilibrium. That's the point. Right? This will be alpha, beta, gamma, three-phase equilibrium. And you can talk about the metastable, right? Metastable. Okay, metastable extension of this two-phase region. Okay, of course, the many roots come out here, like the 180-degree roots, but they all come out naturally with the computation. Okay, because you cannot have this beta and gamma two-phase region inside here. Okay, because you will be conflicted with this alpha gamma phase equilibrium. Okay, so there's many rules where we can talk about later when we talk about the detailed phase diagrams. Okay, so this is an example of a potential phase diagram. Water, H2O, temperature, pressure. So you have the pressure and temperature. So you have a single phase region here, ice, water, and a vapor, right? And you have two phase regions here. This is between ice and vapor. You got this line. Again, this line can be represented by the Clausius-Clapeyron equation. Okay? And then you have the water and the vapor. And they have the ice and water. So there are two very important switching features. First, these two lines, two phase regions, they are all positive slope, right? That means the high temperature phase has larger volume. Okay, vapor has larger volume than the ice and water. However, this two phase region between ice and water is negative. Then immediately we know that, oh, water has smaller volume than ice, right? That's why water has negative some expansion at some temperature range. Not everywhere, right? But some temperature pressure range, water has negative some expansion. Okay. The reason, not the reason, why sometimes you can say the reason or not. But you can see that we can understand this one because you have the negative slope of these two phase regions. So that's a very important feature. Another important feature is critical point. Critical point means that you have two separate homogeneous phases, water and vapor. And if you move the pressure above this 217.7 atmosphere pressure and temperature above 374 degrees C, and then they become one phase. They merge together into one phase. The property cannot differentiate anymore. Okay. Now, if you start with in this region, right, or any region here above this one, you will see that the system, while it looks like it's called supercritical fluid, it's like one phase, homogeneous, right? Well, remember that we define phase as a homogeneous body, which you have this potential Euclid-to-Helm equation to represent it. And if you come down here, the system becomes unstable. It's separated into two phases, okay, into the water and the vapor. Each of them is homogeneous. Okay, so it depends on which direction you look at it. If you look at it from the top down, it goes from the stable to unstable bifurcation. Okay, so that's what I'm talking about it. First, I want to emphasize that all geometric features on this diagram are phase regions. Okay? There's no phase boundaries in potential phase diagrams. We'll talk about them again more when we talk about the details of model phase diagrams. And at the critical point, the homogeneous system changes from stable to unstable and bifurcates into two homogeneous stable phases or subsystems, sometimes we call it, the water and the vapor. And when the system becomes unstable, we know that conjugate variables derivative becomes 0. But before it reaches that point, it's positive. So from positive to 0, that 0 is positive. That's very important. Because you inverse it, you get the property is molar quantity, right? Okay, molar quantity. Molar quantity, for example, in this case, if you talk about the temperature and the entropy. So entropy to temperature will diverge positively. Yeah, maybe I should write it here, right? This would be entropy to temperature. Okay, so maybe I can write it here. Let's see. I have it here. That's right. I can write here. So it will be like a ds, okay, divided by a dt will be equal to plus infinite. Okay, so that means the system diverges. Same thing for the volume, right? Volume to the minus p derivative will be positively diverge. Okay, so that's a very important concept. All right, I need to remove this one. Okay, so remember, this is the conjugate variables, right? Temperature, entropy, minus p, volume. However, for non-conjugate variables, it will also become 0, but we don't have the rules to say it must be positive or negative. Okay, so it could be positive, could be negative. Okay, that's the negative sum expansion we're talking about. Okay, so that means that if you inverse it, the property could diverge positively or negatively. For example, volume to temperature. Volume to be some expansion, right? Some expansion. That means that some expansion could be either positive or negative. That's the critical point. Okay, so this is the property we discussed in lecture 6 too, but now it's the 53 slide, this one. So this is potential, right? And these are the molar quantities. So diagonal terms, there has to be always positive in stable system. So when it diverges, they diverge positively. Okay. However, for other properties here, right, that between the temperature and the strain or volume, okay, they're not conjugate variables. So that means they could be diverged negatively. So we have we developed this entropy theory to predict it, as we have discussed later in this lecture series. And of course, they're symmetric based on Maxwell relation, and the red ones, the diagonal must be positive. The off diagonal ones could be positive or negative. Okay. All right, so that's very, very important. And so what it means, the importance is that you observe some phenomenon which can always go back to thermodynamics to understand it. And then by predicting the free energy, we can calculate those properties. Okay, now it's also not interesting about this critical point is that in the direction from one phase, single homogeneous one to non-homogeneous, talk about instability, right? Because we can calculate it. However, if you move from the two-phase region into single-phase region, there's no instability, right? It's simply just the liquid and the vapor, they move together, become close to each other, then they become one. That's purely mixture. There's nothing about instability, right? No instability involved in this process. So that's very important because it's the same critical point, looking from the single-phase homogeneous to unstable, right? Or from another direction, looking at from two-phase mixture and merging into one. Okay, and they give different pictures, but it will present the same phenomenon. So that's again very important lesson in science is that look at one phenomenon from many directions to get a complete understanding of that phenomenon. All right, thank you very much, and see you next time.